Today's topic is, once again, those types of liquid chromatography. We have a little piece to pass there. But before I continue there, then I show the one textbook, which I found very good. And in a way, it's a classical book for liquid chromatography. So the same author has issued several books, so you can check all those others too, but quite some of those materials that we have in the slides are from this book, so I really recommend this one. Okay, and a couple of more things before we continue with those chromatography types. First, last time there was one additional question regarding alumina and zirconia stationary phases and how they can be used as anion exchange or cation exchange stationary phases. So I promised that I will find a short answer for this. And to tell the truth, it wasn't that easy because first of all, the library is closed, and I know one book there which probably contains the information, but as the library is closed, then I couldn't get there. Searching online, then it appears that those works dedicated to this type of chromatography dated back to 70s, 80s, last century, and most of those articles are not accessible to university subscribers. Therefore, it took some time, but I finally found it wasn't exactly for alumina stationary phases, but titanium. So titanium dioxide. But the same applies also to alumina, so aluminum oxide, and zirconia, so zirconium dioxide. And the point is that those metals on their surface, they form hydroxides, and those hydroxides can undergo two types of dissociation. So first it may undergo dissociation like this, and another possibility is like this. So first equilibrium shows how it can act as a cation exchanger, and second shows how as this metal stationary phase can act as an anion exchange medium. So not that complicated after all. Well, just as a side note to those metal hydroxide stationary phases, they have interesting properties. Sometimes, for example, this zirconium dioxide, this forms very stable complexes or compounds with phospholipids, which means that if the solution contains phospholipids and we analyze or use the zirconia stationary phase for this, then those phospholipids are absorbed there almost permanently. And this means that after some time, the properties of the stationary phase are so much different from the initial one that we cannot use it anymore. So the sample must be free of phospholipids before starting to analyze any samples, which can be challenging, if not reasonable in some cases. And this makes use of such columns quite tricky. It may work in some specific application, but compared to C18 columns, where you practically pass whatever you have in mind, and afterwards wash the column and it's regenerated, and then those are more tricky. So there is more chemistry in this, I would say. Okay, so I think the person who asked the question is not actually here. He's online. So yes. So did you get the answer? Okay, wonderful. All right, and then the second topic is those papers. So I will give them back to you, and then let's go and have a look at those replies that you had. Komal Wasim is here now. Right? Oh, yeah. No. The rules are such that we cannot give any text to other persons. Geo. Okay. Yeah. And my time. So, I think to most of you, I didn't comment much. I just wrote okay. And this means that it was okay. Maybe something was missing, but that's why we go through those questions once again here. So here is the exercise. So I now included those questions in the slide. So first question was about the type of liquid chromatography. And practically all of you said that it's reverse phase chromatography. And I think nobody specified more in detail whether it's reverse phase chromatography with ionization control, or maybe ion pair chromatography. So can you specify it now? We go back to the previous one. So how do you think? With ionization control? Sorry? Yes, first one. This first chromatogram. But no, okay, so you mean the first from this list? Yes. So just reverse phase and with nothing, or with ionization control? Okay, so you mean that this hydroxyl group might donate, or the phenolic group might donate proton? At which pH would this take place? Yes? Yes, for most column that's too high. So in principle, possible ionization control, but it's very likely no ionization control there, just because it works without it. Okay, others had to look in the papers what ionization control means, right? Okay, yeah. So this was the place to remind it. If the compound has acidic or basic groups, then ionization control is necessary. In this case, phenolic group is so weak acid that most probably we cannot reach that high pH, and therefore it's without ionization control. Normal phase, why did you think that it's not normal phase? Most of you correctly explained this, so let's try to explain once again. Why can't it be normal phase chromatography? Exactly. So for normal phase chromatography, the most polar compound in those would be with longest retention time. Yes, the order evolution is wrong. So order evolution tells us that it's reversed phase chromatography. I listed also other possibilities here. So hydrophilic interaction chromatography, again, the order evolution is wrong. Ion exchange. Right? No ions. No ions, exactly. Size exclusion chromatography. Yes, the size difference is too small. What about the retention order? Opposite, yes. The bigger one should elute first and the smallest last. So we end up with the only possibility is reverse phase chromatography. Okay, then next question was order of retention. As I mentioned, practically all of you mentioned or had correct reasoning here. So yes, the last one, the latest eluting one, is least polar, and that's exactly the way it happens in reverse phase chromatography. Then about peak width and peak symmetry, perhaps this was the most difficult one. So regarding peak symmetry, I just wanted you to look at the peaks and think of symmetry. And even if you said that with naked eye, all the peaks seem symmetrical, then this is fine. So just that you considered peak symmetry. In principle, you could have also added that, considering that those compounds do not have ionizable groups, then it's quite logical that in reversed phase chromatography, the peaks are symmetrical ones. If there were some ionizable groups, then quite likely the peaks would have been tailing. Okay, but peak width, and here, yes. Have a question or?
Like, can you remind me why if it is like an ion there, it will not be symmetrical?
Yes, because then there is a possibility of two different retention mechanisms.
Yeah.
One is the usual reversed phase way, and another is ion-ion interaction. And as soon as we have two different retention mechanisms, then it's very likely that the peak will be tailing. All right, and then the peak width. Most, I think, of you noted that in the first chromatogram, the last peak is the widest, and the first one is the narrowest. And this is typical for isocratic elution. So earlier peaks are narrower, later peaks are broader, and indeed this happens with isocratic elution. So far we haven't discussed gradient elution, and that's why we haven't used also the word isocratic elution. But so far we have considered only isocratic elution. And this is typical that in that case, the later eluting peaks are more broad. So from this picture, it was evident that it's isocratic elution because the later eluting peaks are broader. Yes?
What is the reason for that?
We will discuss this when we discuss gradient elution. We have a separate lecture for this, and then we go more thoroughly through this. Okay, and why does it happen that later eluting peaks are broader? Well, Van Dieter equation is to blame here, or is the reason, and especially this second term, or this B term in Van Dieter equation. So the more time we give to the diffusion to take place, the broader the peak will be. And we're speaking about longitudinal diffusion, so along the column, along the flow, and to the other direction or the back direction of the flow, the diffusion takes place, and the more time it has, the broader the peak will be. So there was no question, but how could we get the peak for compound number 4 narrower? Then the solution would be whatever it takes to elute it faster. So the faster it elutes, the narrower is the peak. Okay, and then what change resulted in the chromatogram number 2? And now there were many possible reasons given, and I added some. So higher eluent flow rate. How do you think? Can this be the reason? Definitely, it will make the retention times shorter. But let's imagine that we make the retention time, the eluent speed or flow rate 2 times higher. So what would happen to retention times of the compounds? Yes, but they will elute earlier, definitely, right? Mm-hmm. but is it 2 times earlier, or how the ratio will be? The flow rate is 2 times higher. Two times as well. Okay. Check this general elution equation and find this out for next time. So try to figure it out. Wasn't very sure about it. Okay, so this is one possible explanation. Then another was that column was changed so that the new stationary phase is used, and this is less non-polar, or to word it other way, than more polar stationary phase. Would this result in shorter retention times? Yes, this would result in shorter retention times. We will see this also in next slide, in next lectures. Shorter gradient. Well, as the first chromatogram was isocratic, well, the second one maybe not that obvious, but the latest peak is also wider than the first one. Therefore, it's not a gradient elution. So, in principle, possible, not completely wrong, but not likely. Okay. Then higher concentration of strong eluent component. I think this was what majority of you wrote, and this is exactly what actually was done to obtain this chromatogram. Then eluent with stronger organic modifier. So let's say if the chromatogram number 1 was obtained with methanol as organic modifier, then when using acetonitrile instead of methanol, then also the retention times would be shorter. And even more so if we would use tetrahydrofurane, then the retention times would be even shorter. Again, this is the topic of the next lecture. Then higher temperature. Well, perhaps the difference is too big. So in principle, the higher temperature makes retention times shorter, but not 2 times shorter. So the effect is bigger than could be explained by temperature. Different pH of the eluent. How do you think? Different pH of the eluent. Again, topic of our next lecture is that pH is a very powerful means of changing the retention time of compounds. But we also have considered it already, so could this be the reason?
Of the good but we have seen like the pH like too big. So
yeah, that's right. So as the compound, we don't consider those compounds ionizable, then pH should have no effect in this usual range. Okay, and well, we could think of other means, shorter columns, for example, or column with smaller volume, internal volume or something. but yeah, in fact, it was just that the concentration of stronger eluent component was higher in this case. So, yeah. Yes, these would be wider, yes, that's right. But the times would shift a bit earlier because just, yeah, sure. Yes.
Like when we're talking about liquid chromatography, what will have a bigger impact, like increasing the flow rate or in changing the composition of the mobile phase? Like, because it's a, what I have learned is like in gas chromatography, you should increase or decrease the temperature in order to change the rotation time. But for liquid chromatography, was the composition of the mobile phase. So what would have a higher impact, the flow rate that you are using or the
And impact on what?
the retention time? Like,
Retention times. Well, the easiest is to change the flow rate. Double the flow rate and the retention times will be shorter.
but can you, with all of the compounds, do we like have, or can you do with like with the same with the gradient that for that compound like maintain the same composition and for the camphoplastics that is too hard, then change the mobile composition? Can do the same with the flow rate?
Yes. In principle, yes, but flow rate is very seldom altered in liquid chromatography. In most of the cases, just constant flow rate is used, and the composition of the eluent is what varies. So, yeah, in literature there are examples where the composition of the flow rate has been changed during the run, but yeah, that's a rare case. Mostly it's organic modifier that is changed, the %B. Okay. So I think this was a good exercise. All right, and now let's go to this final small chapter of types of liquid chromatography. And our last topic from this one was size exclusion chromatography, but now we continue to chiral separations. So chiral separations is about stereochemistry and just a very brief and superficial introduction to stereochemistry. If we have enantiomers, so enantiomers means that the compounds are mirror images of each other and non-superimposable. So as an example here, we have two forms of tartaric acid, so two enantiomers, and we see that in the first one, the upper OH group is in front of the figure, and this is behind the surface of this slide. And here it's the opposite. So the molecules, as shown here, they are mirror images of each other, and those are not superimposable. So those compounds have same physical and chemical properties, so everything is the same. Solubility is the same, all boiling temperatures, crystallization points, everything is the same. There is just one parameter which is different, and this is the direction into which those solutions rotate the plane of polarized light. So if we illuminate polarized light, through the solution of one enantiomer, then it turns the plane of the polarized light into one direction, and through another enantiomer then to the opposite direction. So the nomenclature for those enantiomers, there are different ways, R and S and D and L and plus and minus. So we do not go into this nomenclature. Let's just accept that those exist and used to differentiate between enantiomers. Now, there is also a diastereoisomer or diastereomer. Diastereomers are molecules which are non-superimposable, but are not mirror images. And in this case, if we take this mesotartaric acid, then it's non-superimposable to L-tartaric acid or D-tartaric acid. And at the same time, it's not the mirror image of either of them. So mesotartaric acid is different from this L and D tartaric acid, but it's not a mirror image of either of them. And diastereomers have different physical and chemical properties. So I didn't list those here, but the molecules in general can have different boiling points, different melting points, different solubilities. Everything can be different. So the differences might not be too high, so too big, but still they are different. And very often this difference in physical properties is sufficient to chromatographically separate diastereomers. So usually diastereomers can be chromatographically separated, but enantiomers cannot be. So that's the point at the moment. So enantiomers we cannot separate with usual chromatographic systems. Diastereomers can be separated. So, and all the question about chiral chromatography is how to separate enantiomers. And the key here is to create diastereomeric complex. So from enantiomer, we create a diastereomeric compound or complex. And as it's diastereomer now, it has different physical chemical properties and can be separated. So how we can achieve this? We need one more chiral compound somewhere. This chiral compound can be a component in a mobile phase. So if we have, let's say, one chiral compound as a mobile phase additive, which forms complex with D or L tartaric acid, as we have in the example, or D or L form of whatever molecule, then the formed complex is diastereomeric and can be separated by chromatography. So additive in mobile phase is one way. Another is that we have chiral liquid stationary phase. So the stationary phase is chiral. Then the solid stationary phase can be also chiral. And finally, we can derivatize chiral or those two enantiomers. We can derivatize them with chiral reagent, and the result is diastereomeric molecules, two of them, which can be separated chromatographically. And one example is shown on the next slide. So here, first, the analyte is ibuprofen. So this pharmaceutical ibuprofen, which has a chiral center here. So there are two enantiomers of ibuprofen, R and S enantiomer. To separate them, then in this example, derivatization was carried out. So derivatization reagent also includes a chiral center. So it's a chiral molecule, and derivatization reagent is just a pure enantiomer. So it's not a mixture of two enantiomers, it's pure one enantiomer. And if this optically pure enantiomer reacts with ibuprofen, then the result is two kinds of molecules. One is R, this R isomer, and another is S isomer, but now derivatized with this one chiral enantiomer of reagent. Therefore, those R and S are not enantiomers anymore. Now they are stereoisomers, and therefore can be separated chromatographically and in quite normal C18 column using usual eluent systems, so in usual conditions. Okay, so far so good. No questions? No? Sounded like boring. No? Okay, maybe you know this already. No? Something new. Okay, that's good. All right, then let's continue. The stationary phase can be also chiral. So in that case, chiral compounds are bonded to the stationary phase, and abbreviation chiral stationary phase (CSB) is quite often used. And in dedicated in the chromatographic literature, which is dedicated to chiral separations, then quite often this CSB is just given without any explanation. It's regarded as a common knowledge. There are different types of chiral stationary phases. We only have a look at this brush type CSPs. And what is uncomfortable about those stationary phases is that if we buy one column, chiral column, then it maybe works for particular problem at hand that we try to separate, and it's not able to separate other enantiomers. And predicting which columns or which stationary phases are suitable for separating different enantiomers, this is quite impossible. So people mostly just test, buy several columns and test which one works for particular mixture. Okay, but what about this brush type CSP? So brush type, or sometimes called Irkle type CSP, those stationary phases are designed according to so-called 3-point rule. So there should be 3 points which interact between the analyte molecule and the stationary phase molecule. And in this example, we see that there is one dinitrophenyl group where there is which is so-called pi electron deficient group. So that if the analyte contains any large pi electron system, then this interacts with this dinitrophenyl group. On the other hand, it has phenyl group, which provides pi electrons for interaction. And if the analyte molecule has pi electron deficient group moiety, then this interacts with this part. And then we have several locations where hydrogen bonding can take place. So amino groups and carbonyl groups. So hydrogen bond donating and accepting groups. And so 3-point rule means of course, and then this stationary phase molecule itself should be pure enantiomer. So it has a chiral center, and it has to be enantiomerically pure, this stationary phase. Okay, and what happens is illustrated here. Here, this is another example of this Kirkle type stationary phase molecule. And we have two molecules of analyte, so two enantiomers. And we see that this S isomer in this case can interact with the stationary phase in 3 locations, but R isomer can interact at 2 locations, but the third one is geometrically not favored. So it just doesn't reach this third point on the stationary phase. As this R isomer has less chance of interaction, or the total interaction is weaker with stationary phase, then this elutes first, and this S isomer has longer retention time. Now, perhaps one interesting point to note here is that in this example, this R isomer has short retention time and S isomer has longer retention time. How could we reverse this order? Yes, to what?
By changing the chirality.
Yes, sorry? Yes, exactly. So there are 2 enantiomers for the stationary phase molecule. We can just use the other enantiomer. So this is very important in pharmaceutical industry, in pharmaceutical analysis. But let's discuss this based on the next example. So here is an example of chiral separation of zolmitriptan molecule or the pharmaceutical, and we see that R enantiomer has shorter retention time and S enantiomer has longer retention time. So now we can imagine that if the peak order would be reversed, so that this S enantiomer would elute first and then the R enantiomer, then if this first eluting compound has, or the peak has a bit of tailing, then it would overlap with this enantiomer. So tailing is quite common in this field. Therefore, it's always a good idea to have the low amount or low fraction of enantiomer is eluting first, and the main compound eluting later. Then we don't have the danger of overlapping this tail of main compound with the low content enantiomer. So, thanks to the possibility of easily reversing the order of enantiomers, then this is a good way to do this. All right. So this was our last slide about chromatography types. Any questions? Why did I pick this example?
Yeah, not example, but like this material.
Well,
There are like many others, like
yes, brush type is most common, but well, I would say that the rest is largely experimental, and mostly we see them in scientific literature. But this kind of stationary phases, those can be found also in pharmacopoeia materials. So in those, let's say, official methods. Okay. No further
These
questions?
methods have been previously validated.
Sorry?
These methods have been previously validated. That's why it is more common.
Yes, I think so. Usually in pharmaceutical industry, if it's about enantiomers, then the producer or the manufacturer of the pharmaceutical has to develop methods and also make them available, so that those analytical methods must be available. And yeah, well, of course they try as simple and universal methods as possible, because most industries have many products, many pharmaceutical compounds. Okay. If there's no further questions, then let's take our next topic. And next topic is about method development in liquid chromatography. So we take the most common case, small molecules, reversed phase chromatography, and, well, for quantitative analysis. One more thing to add here would be that we focus on isocratic separation. So the eluent composition during the runtime does not change. Now, one thing that is useful to remember while developing method is that it's always possible to improve methods. But at some point, we just need to stop developing and start using it. So develop it until it's good enough, and then just work with it. It's always possible to make it a bit more shorter, a bit faster, a bit more economical or something like this, but we need to use it. Now, as this sentence says, until it's good enough for the aims. So first of all, we have to define what we aim at. So what is our aim, or what are our goals? So first we have to define goals. Then we gather information about the analytes and samples. Then we need to obtain initial chromatogram and then need to refine it or to optimize it. And the final step would be validation. Well, we just mentioned that the method has to be validated, but the whole validation process is too long to be described in this course. So there is another course for this. So first, defining the goals. And for this, we need to understand exactly what needs to be analyzed, what are the analytes, what are matrices. And quite often it's good to know what for the analysis is needed. Well, it depends on who requires the analysis. Well, sometimes if we develop method for somebody else, then it's useful to ask, please explain me exactly what for this method will be used and what for those analytical results will be used. Sometimes the requirements to the final method are dictated by some regulatory bodies. It may be pharmacopoeia, requiring, for example, that the preparation of peaks has to be at least 1.5 or maybe even higher. For environmental analysis, usually this limit of quantitation is the crucial parameter, and then we have to demonstrate or be able to demonstrate that we can analyze concentration of sufficient low concentrations. Sometimes sample size is limiting. We have worked in a situation where we had less than 50 microliters of sample available. And this means that the sample preparation for the method has to be very well tuned so that we can use a sample and there is no room for mistake in that case or repeated analysis. Then sample preparation is often part of the method or generally is considered as part of the method. And therefore, sample preparation ideas should be already in mind. Then we have to decide what kind of calibration to use, internal standard, standard additions, matrix matched, so what calibration will be. Then number of samples. Well, it may seem that how does this affect the whole process? It doesn't matter how many samples we have to run. But in fact it does. If we develop a method we know that there are just 10 samples to run for which the results are needed, then, well, it's not worth spending 2 months on optimizing the method as short as possible, because for 10 samples, it just doesn't give any real savings. But if we know that we need to analyze 2,000 samples, then indeed it's worth investment into making the chromatographic run as short as possible. Every minute is multiplied by 1,000, and this is a lot of time. Okay, number of analytes and number of matrices. Quite often the method is used for more than one analyte. So, for example, in pesticide residue analysis, very often 5, 10, 20, 200 analytes are of interest. So we have to be prepared then for analysis of all the analytes. And number of matrices, coming back to the example of pesticide residues, then it's quite different whether we analyze pesticide residues in lettuce or cucumber. They are very different matrices, and if we want to develop just one sample preparation process for both of them, then it's gonna be a lot of work, because developing it for both matrices or even more matrices at the same time is very demanding. So sometimes we develop the method and use it on the same instrument, but sometimes there is a department of method development, and the method is then transferred to another department which actually uses the method. In that case, we have to consider both instruments, whether the instruments allow transfer of methods easily, or we have to adjust the method in one instrument so that it can be really transferred to another one. Time frame of the method usage, whether it's just we use it next week and then forget about this, or maybe it is meant for routine use for years and years. Then, of course, the method development should be more elaborate. Operator skills, if we know that operators come and go and maybe are not very skilled, then the method has to be more robust. But yeah, again, it depends on the time frame. Then next step, we have to gather information. So one needs to go through the literature and then once again through the literature. So search not only internet, but also consider books and colleagues, because as one our old colleague used to say, a day spent in the library can avoid months-long senseless testing in the laboratory. So this was one legendary chemist at our department. He passed away perhaps 7 years ago, if I'm not mistaken, at the age of 96. And he was actively working in chemistry till the end. So a legendary man indeed. Okay. Then information about analytes, name and structure, stability. Well, there are compounds which tend to decompose easily, so we want to be sure that it doesn't decompose before we start to analyze it. And there are quite tricky compounds which really don't look like unstable, but they are. pKa values, clearly for knowing in which ionic form it is, then pKa values are needed. Solubility, and solubility most importantly in those solvents that we use for eluent. And one very important thing is that the solubility is pH dependent. And we not recently, but a few years ago, we ruined one column because we didn't take into account that the sample was at very high pH, and when we injected it to LC column, then it met this acidic mobile phase, mixed with it, and precipitated. It precipitated in the column where it just the column was stuck, and stuck so strongly that it just died, this column. So yes, be careful with those solubilities. For detection, one has to consider what detector will be used and whether the compound that is analyzed has suitable properties for that detection. So for simple carboxylic acids, probably ultraviolet visible detector is not suitable, but also it's quite likely that mass spectrometer is not suitable for short chain carboxylic acids. Then what kind of ionization we can use or has earlier used for that kind of compounds, and what fragments were observed in mass spectrometry. So if LCMS is used, then it's better to have this information at hand before going to lab. More collection of information, sample type. It's very different if we analyze soil or tissue or pharmaceutical preparation, whether it's brought to the laboratory as just a nice pure solution, or it's in mixture, or maybe it's still in a solid sample. As mentioned already, the amount of sample available, so what kind of sample preparation we can perform. So again, solubility of the sample, which solvents the sample matrix is soluble and where not. And also typical sample preparation procedures. There are quite, let's say, generally applicable procedures for, let's say, blood and urine samples, and also fruits and vegetables. The sample preparation methods are available. Okay, and now the fun part, I would say, starts here. So obtaining initial chromatograms, we should make the decision on what type of chromatography to use. And for this lecture, we assume that it is reverse phase liquid chromatography. Detection may be ultraviolet visible absorption, maybe fluorescence detection, maybe mass spectrometry. Well, it ends with 3 dots, but, well, can you name some more detectors? Sorry? Electron capture was in gas chromatography. Yes, in LC. Refractive index detection, yes, but this requires usually higher concentrations than others here. Okay, something else? Yeah, this is not exactly dispersion, but scattering, light scattering detectors. Yes. Yeah, that's ELSD. Yes. I see. Okay. Refractive index and ELSD. Yes. This ELSD stands for evaporative light scattering detector. Okay, more? Electrochemical, yes. Have you worked with electrochemical detector? Okay, okay. Electrochemical is tricky. Okay, yes, there are more detection possibilities. Okay, choice of detector depends on which ones are available, which LOQ is required. If very low LOQ is required, then refractive index detection is out of question, for example. Then ionizability. If mass spectrometric detection is available, then maybe the compound is not ionizable, cannot be detected by mass spectrometry, or maybe it's ionizable by some other ion source than available. Ultraviolet absorption. So if spectra was obtained from the literature search, then now the absorption wavelength is handy. Okay, starting point for this initial chromatogram. Usually C18 columns are available in the laboratory. pH most probably or usually in the acidic side, and usually pH around 2 or 3 is used as a starting point. If UV detection is used, then phosphate buffers are suitable. But for mass spectrometric detection, phosphate buffer is not suitable, and volatile buffers must be used, and most common one is 0.1% formic acid. So here you can see is the mistake of definition. So buffer solution and formic acid. So formic acid alone is not buffer solution by definition. But it's quite common in liquid chromatography that we speak about formic acid or acetic acid solution and name it or list it together with real buffer solutions. So just we all know that it's not fully correct, but let's go with the flow and use the same term. If the analytes have basic properties, then it's possible that we need to adjust pH of the eluent higher than 8. And in that case, the column has to tolerate that high pH values. Those columns are available. Just we have to check whether the column that we have in our instrument can resist this pH or not. Then, as eluent, the strong eluent component, acetonitrile and methanol, are often used. Acetonitrile has advantage of being less viscous in mixtures with water, and therefore the pressure in the column is lower. On the other hand, methanol is cheaper, and therefore methanol is quite often the first choice. THF, tetrahydropurane, is occasionally used. It's not usually the first choice, but can be used. If you decide to use THF, then be careful that those capillary tubes made of PEEK, polyether ketone, polymeric tubes, those tend to swell because of THF. Therefore, pure THF should not be pumped through those tubes. All right, then we need to record the first chromatogram and then start to optimize it. So what parameters to check, what to optimize? And here the resolution is the first parameter, and asymmetry of peaks is the second one. So resolution by itself contains retention factor, selectivity, and efficiency. So it takes all those three into account. Asymmetry, well, as we know already, then asymmetric peaks are obtained if there are more than one retention mechanism available, and therefore if asymmetric peaks are obtained, then we have to suppress this second retention mechanism. Okay, so in the following slides, we focus on optimizing the resolution. So the equation for calculating the resolution is shown here. So it has three terms. And the first term is so-called retention term, and this depends on the retention factor, K, so K divided by K plus 1. Then there is selectivity term, the second one, and alpha minus 1 divided by alpha is the definition for the selectivity term. And efficiency in terms of plate number or plate count. This is in square root. So this is the third term. Well, as this peak resolution, this applies to two peaks, then in fact we have to consider two retention factors, and the question arises, which one? And there are several ways of deriving this equation. More strictly, or let's say one way of defining it is via this retention factor for the second compound, later eluting compound, so K2. And the number of theoretical plates also for this second peak. But in general, most sources in discussing this method development, they only stick to this kind of simplified equation. So to see the rigorous or more strict derivation, then you can check this article. Okay, but we will continue with those terms. We use those numbers first, second, third in following slides, and go one by one and see how to affect those. So how to increase or decrease any of those terms. Okay, now if we consider the retention term, then it contains retention factors. And we know that retention factors should be higher than 2 and smaller than 10. Well, in some cases, it's also acceptable if it's between 1 and 20. But yeah, well, we preferably would like to see it between 2 and 10. Why so? Because if K is smaller than 2, then the separation is just affected a lot by the sample solvent and also small changes in mobile phase, and also interfering compounds from this early eluting peaks. They may also affect the signal of the peak, of this analyte peak, eluting too early. So K should be bigger than 2 and smaller than 20 or smaller than 10. Well, why is this upper limit? Exactly. So if K is too high, bigger than 20, then we most likely we're just wasting time. Too long time. Okay, but how does the retention term affect the resolution? So in this resolution equation, if we consider that number of theoretical plates was 1 and also the selectivity term would be 1, then this would be the RS value. Okay, so and if K is between 2 and 10, as shown here by green line, then in this range, the RS value increases from 0.65 approximately up to 0.9, let's say like this. So quite a significant increase. If we compare once again, in this point, the K value is 1, so the retention factor is 1. Here, retention factor is 3, and and this causes a 1.5 times increase in resolution. So if we manage to push the peaks further, then the peak resolution, so the separation of two peaks, improves 1.5 times, which is significant improvement. Now, if we consider changing retention factor from 10 to 20, then it would only increase the peak resolution by 5%. So 50% here, 5% here. So very different effect. And retention time in that case would be approximately 2 times longer, which is a lot. So a lot of time for very small change in peak separation. So if we can make changes in this range, then the effect on resolution is significant, and after this, the effect on resolution is not that big anymore. Okay, here, how much do we lose in retention time in that case, or losing time? So retention factor increases from 1 to 3. So how much longer is the total runtime or the total retention time? Oh, sorry? 3 times? Maybe. How do you know? Or why do you guess? How is this K calculated, this retention factor?
like the difference between the rotation time of the analyte minus the dead time.
Um, okay, so let's mark TM here at the moment. So the void time or dead time, yeah. Okay, and K is, let's say this is peak number 2, peak number 1. This is TR2, TR1. K2 equals TR2 minus Tm divided by Tm, which means we are speaking about this distance, which is TR2 minus Tm divided by Tm. Okay. So going back to the question, so how much longer would be the runtime if we increase K from 1 to 3? It's easier if we just assign some numbers. Let's assign a number 1 minute here. What does K equals 1 mean now? So K2 equals 1 means that TR2 equals two. Two first time, two second time. Well, so okay, 2 minutes. All right, and if K2 equals 3, then what would the TR be then? TR2. First, second, and third time. Okay, so if the retention factor increases from 1 to 3, then the retention time grows from 2 minutes to 4 minutes or increases 2 times in this case. Do you agree? Maybe. Or for sure? Yeah? Seems that you're hesitating for some reason, no? Okay, yeah. So the difference is just 2 times in that case. Okay. So a comment from internet? No? Okay. All right. Let's continue then. TM will not change. No, TM will remain the same indeed. So as long as the column is the same and eluent flow rate is the same, then the TM remains the same. Okay, now how to optimize retention? Practical. Practically, we would start from, let's say, nearly 100% of organic eluent component, and then reduce the organic concentration in steps of 10%, so 90, 80, 70, and reduce the organic concentration in the eluent. And if suitable K is found, then we can fine-tune the percent B further. Okay.
What do you mean by fine-tuning?
Fine-tune. As we move in steps of 10, then fine-tuning means that we can set it precisely to the desired value. If we want it to be exactly 2.5, then by tuning it, let's say, at 57%, then we can make it be equal to 2.5, this retention factor. So this can be done all experimentally, so that we just go one by one and test different eluent compositions. But in fact, there is a mathematical relationship between percent B and logarithm of retention factor. So logarithm of retention factor depends more or less linearly on the percentage of organic eluent modifier. So relationship is shown. And now the question to you is, which organic phase concentration would yield suitable retention? Which organic phase concentration would yield suitable retention? So which organic phase concentration we should use in our final method? Not one point, it's a range. But how to find this range? More than logarithm K is more than 2. Sorry? K value. Okay. So please tell me the number of percent B. Maybe it helps if I say that logarithm of 2 equals 0.3. Maybe this helps somehow. I don't know. Okay. So logarithm of 2 is 0.3 is approximately here. And k equals 10, then logarithm k is 1. So we should remain between 0.3 and 1 on this vertical axis. And now just read the percentages here. So it's about 52, maybe 52 to 70 something. Yeah. From 50 something to 70 something. Okay, what is even better is that if we make the first measurement and we get some reasonable retention time where the k value is already bigger than 0, then we can put this %b here and the found logarithm k here, and s just an estimate is 3, and using this data we can already start to estimate what could be the next or suitable percentage of organic phase. Yeah, just from very few experiments, even if we do just 2 experiments, then we get %b, we get logarithm k, and by knowing that s often is approximately 3, then we can already start drawing this line. Very interesting mathematical problems, right? I think it's 8th grade. But nobody said at 8th grade that it's going to be useful at the university. Or how to use it. Okay, anyway, we are over time. Exactly where it turned interesting now the time is over. So, any questions?
Where does the S come from?
It's mostly just an observation that for small molecules, it's mostly in this range. It's relatively variable. Yeah, from 2.5 to 3.5 easily, and it's not that constant. But anyway, it's for first estimate, it's good enough. And after we register the second point already, then we don't need the slope value anyway, and we can continue with our experimental slope value. Okay, but then thank you and see you next week. Those of you who posted this this analysis of chromatogram that some did here in the lecture hall, some sent by email, then I will go those and send those also back with a bit of comments, even if it's just okay. Okay, thank you and see you next week.